Hello everyone, welcome to Knox Game Design for September 2023. My name is Levi Smith. So this month we're going to be talking about OpCodes. This is something that I really didn't have much exposure to until I got to college. I kind of wish somebody had introduced me to some of the lower level computing concepts before I got into like a full computer science program. Back when I was in high school, basically all we had was word processing and basic spreadsheets. So just wanted to share this just as an introduction maybe for people to how things work under the hood in your computer. So many people probably know there's programming languages. That's how you write games. And I'm going to try to tie this into game development as well. So, you have a programming language such as C or C++ or C# or Python or Ruby, whatever. That's typically how people write programs in a high-level programming languages. So that program gets compiled into assembly code. And assembly code is kind of like what ties your program to the actual machine code that runs on your processor, the ones and zeros. So once it gets compiled into assembly, it basically has the step-by-step instructions that will be run on the processor. So you can take that assembly code, which is still somewhat human readable. You have what they call OpCodes for each statement with a number of parameters. So that assembly code gets compiled down into machine code, which is basically the ones and zeros that gets written into assembly into a image file, which is your executable. And I'm not going to get into how the executable gets loaded into the processor, how it's executed. That's a topic for another day, but that's another low-level thing that I really wasn't exposed to in high school, which I wish I just had a little bit of exposure to it before starting the computer science program. Okay, and this is one way I'm going to try to tie this into game development. So each game console, so I'm going to go back to the 80s to my first console, the Nintendo Entertainment System, which I've talked about many times. It has the 6502 processor, MOS Technology 6502, which I found was kind of interesting, is actually used by a number of other consoles. The Atari 2600, the Apple II, basically personal computer, is actually used by the Super Nintendo as well and the Commodore 64. So I think not all the 6502 processors were the same, but I think the underlying architecture below is the same. So they all speak the 6502 opcodes and everything, but some of them may had additions added, slightly different. So there are variations on that 6502 processor. So you can't just take a 6502 chip out of a NES and put it in an SNES, and it probably won't work. But I've heard some people say, hey, yeah, you can take a generic 6502 processor and put it in some consoles and it works. So maybe your mileage may vary. The Game Boy, my first handheld console, it uses the Sharp LR35902 processor. The MIPS processor, MIPS actually stands for microprocessor without interlocked pipeline stages. It was used for PlayStation 1, Nintendo 64, PlayStation Portable, and PlayStation 2. Then as we got into the new millennium, everything switched over to PowerPC, which I believe was originally used in the Macintosh and the Apple computers, which is also called IBM Power. Is used in the GameCube, Wii U, PlayStation 3, and Xbox 360. So then, in the generation of consoles after that, they switched over to x86 64 for the PlayStation 4 and Xbox One. So I think that's why, it's pretty difficult to take a PlayStation 3 or 2 game and run it on the PlayStation 4 without using emulation, or an Xbox 360 game, why it's so difficult to port over to the Xbox One. But because it's a different architecture, a different type of chip with different opcodes and different machine code underneath. And now in the latest generation, everything's switching to ARM for the Nintendo Switch. And ARM is also used in a lot of mobile devices, I know, as well. So this is another thing I really wasn't familiar with until I got into college, and it was like a lot at one time. But basically, the processing system, CPU, is called the data path. And on your CPU, you have multiple registers. Registers are kind of like memory, just like temporary memory, that everything in your physical memory has to be loaded into a register before the CPU can actually operate on it. So the operators are things like add and subtract, and then you got different operators for loading into memory and pulling things from memory into a register to do those operations. There's an ALU, algorithmic logic unit, and that's what actually performs the adds and mathematical operations on your data, like add, subtract, increment, and also your Boolean operations such as AND, OR, and XOR. There's also a program counter on your CPU, so that's what keeps track of what step in your program you're on. And then there's the bus, and the bus is what carries the information, the data between the different components like the register and the ALU and all that good stuff. And then there's also a multiplexer where you can have a selected output based on a certain set of input. So back to opcodes. Here are some common opcodes for the 6502. I've used this quite a bit for the NES program that I've done. So as I mentioned earlier, the data transfer to load data from memory, from like a RAM chip, SIM chip, into a register on the CPU. You got your loads, LDA, LDX, and LDY. Then you can take data from a register and store it back into memory with your store commands, which are STA, STX, and STY. So basically you have two registers, X and Y, and then you have an accumulator. So accumulator is basically where the output from your operation gets stored. So typically you'll load two values into your X and Y register and then perform that operation, and then that gets stored into accumulator. That's why it's A, LDA, and STA. Then you can take that and store it back into memory. Your logic opcodes for 6502, you got and then OR is ORA, ORA, and then exclusive OR is EOR. So you can take two values and registers, and you can do a bitwise AND using that AND, or bitwise OR, or an exclusive OR. Then you got your arithmetic commands, ADC, SBC for add and subtract. Then you got your compares, CMP, CMX, and CMY to compare two values, whether they're equal or not. Then you got your increment and decrement values. So that's basically just adding one. So you got INC, INX, and INY, and decrement is DEC, DEX, and DEY. Then you got your control statements. So you got BRK for a break if you're in like a loop. And then you got your jump commands, JMP, JSR, RTI, and RTS. So this, if you want to jump to another point in your code execution, use a jump. Or if you jump to like a sub-procedure, you can go back with RTI and RTS. Basically return from subroutine, I believe that stands for. And then you got your branches. So I think of your branches like your if and while statements. BEQ, branch on equivalent, or BENE, branch on not equal. So you can make like an if statement. So if it's equal, then you can do something. Or if it is equal and you branch on equal, then you can tell it to go to a label to another point in the program execution in your assembly code. Then you got no op. If you just don't want to do anything for that CPU cycle, then you can do a no op, which is NOP. And this is one thing I found out when I was preparing for this talk, is one thing I didn't know is like one opcode may have different values in the machine code. So I guess that's one reason you don't go directly from the high-level programming language directly down to machine code, because an add, I got an example here, an add has 8 different possible values, and I got them listed here in hexadecimal. And basically the reason is because of the way it indexes based on the memory. Like you can have an absolute indexed or a zero-paged index. So that tells the processor. And basically it comes down to, like, you got an add, and you can have like maybe one parameter or two, or different number of parameters for your add opcode in your assembly. So the assembler will determine the correct numeric value, such as here 29, 2D, 3D, 39, 25. And this is all hexadecimal. So it's really 39, 2D, 29, 25, 35, 21, and 31. So the assembler will take that opcode and turn it into the correct machine code instructions. So in this case, there's 8 different ways the processor can do an add. So that's if a human had to go in there and like figure out the correct numeric value for each add, you probably go crazy. So that's why you have one AND opcode for 8 different values. Okay, so here's an example of a no-op. So you can go on to its site, and I believe this is 6502. So the no-op machine code instruction is EA. It's not EA Sports or Electronic Arts. That's basically E in hexadecimal is 14, A is 10. So that opcode is represented by 2 hexadecimal values. And the way you can convert that into binary, I've done a talk about this before. So you look at the E, so that's 16 to the first power times E, which is a 14, plus, and then the A is 16 times 0 because it's in the first position, and the E is in the second position going from right to left. So you do 16 to the first times E plus 16 times to the 0 times A. That equals 16 times 14 plus 1 times 10. I actually got that listed there twice. Get rid of one of those. I don't know. Actually, the first one shows how the 16 to the power is converted into the numeric value. So 16 to the 0 is 1. Anything to the 0 power is 1. I learned that from math team back in high school. Anything to the 0 is 1. That's usually a frequent answer to math problems. But yeah, you take the 16 times 14 plus 1 times 10, that gives you 234. So usually you don't, 234 is what we call decimal, regular human readable numbers that whole numbers that we learned in math class. And typically you won't see 234 in your opcode. It'll get typically represented by the ones and zeros. So 234 in binary is 110. 1010. So that's just to show how everything is represented by a numerical or a unsigned integer value or a binary value. Typically what you'll probably see is like you take the E, which is 16, which is 14, and you convert that into binary, which is 1110. Then you take the A, which is 10, that's 1010. So you can go directly from the hexadecimal much more easily into binary than doing this roundabout way of going from hexadecimal into a decimal whole number then into binary. That's but it's just showing how everything is basically represented by an integer number. So you can see here, there's the EA there. So some of the different processors may have additional no-op operations, but those aren't the official 6502 opcodes for no-op for do nothing. Yeah, it says down here 6 unofficial no-ops do nothing. The official no-op is EA. That's a trivia question. What is EA in 6502? It's a no-op. So we looked at 6502 for like the NES and SNES, Apple II. So what about MIPS for that next generation of consoles? So you kind of got the same thing going on. You got data transfer, you got your logic, you got your arithmetic, you got your control and your branch. So data transfer, loading things from memory into a register. You got LB and LW for loading a byte or loading a word. You got SB and SW for storing a byte and storing a word, taking it from a register, putting it back into memory. Your logic is and, XOR, and or and XOR. So in MIPS, it is possible to have 2-letter opcodes, where 6503, everything was pretty much a 3-letter opcode. I don't know why that is, but maybe it made it easier for parsing, I guess, if you know all your opcodes are 3 characters long. But in MIPS, you can have 2 or even 4-letter opcodes, as we'll see in the control statement. So yeah, you got your logic, your arithmetic. So in MIPS, you have both add and subtract. I think implicitly you can probably do subtract using 2's complement if you don't have a subtract opcode like in 6502. But in MIPS, they do provide a subtract, and also it has MULT for multiply and DIV for divide. So this gets in, I'm just going to mention it because I wasn't familiar with it before, but you got, let's see here, RISC and CISC. RISC is reduced instruction, I can't remember off the top of my head, and CISC is complex. Can't remember what it stands for off the top of my head, but basically the RISC, the reduced instruction set, means you don't have these extra codes like multiply and divide. Everything is just basically kind of like the 6502. You don't have these convenience for like loading and storing. I think CISC, you have convenience methods for doing operations directly on data in memory without loading it into a register. So that's when you get into your CISC architectures. So in MIPS, you also have control statements. So J, JAL, JALR, and JR for jumping. I've never written anything directly in MIPS myself. I think I did something for a MIPS simulator in college a long time ago. Really didn't understand what I was doing at the time. So I can't give you a good example or use case or scenario for how these are actually used. You also have branches. Same thing as 6502, BEQ and BNE, branch on equal, branch on not equal. And as I said, with the 6502, that's basically like if you want to do a while or an if statement. Okay, so x86, my first PC was a 386, so x86 is an instruction set that's been around for a long time with the IBM compatible processors. And as with anything, there's different generations. I know like they had the MMX that was added on for multimedia back in the late 90s. So with your base x86, you have data transfer again, but it's MOV. Logic, you got and, or, and XOR. Just like the MIPS, you got your arithmetic, your add and sub for add and subtract, and mul and div for divide. And then you got control statements, JMP. Then you got a call, ret, and a rep for doing function calls. Again, I've never written anything in x86 assembly directly myself, so I don't have much experience in doing x86 assembly. Most of my experience with assembly is in 6502 for writing NES games. Then you got an NOP for your no-op again. So you kind of see the commonalities between all these different assembly languages. So yeah, how do you know how these get translated into? I didn't make these tables myself, and I'll put like the references I used online. There's a really good site for looking at 6502 opcodes. So basically, the first hexadecimal digit is on your left side, and your second hexadecimal digit is on the top side. So if you look at like your first row and first column, that's 0, 0. That's your break statement right there. You can see it right there if you zoom in. BRK. Like your no op, you go down to your E on the left side, and then the A on the top side. That gives you your no op EA. But then, as you can see, like with your AND, it's a 2, 1. So that's AND. But also you got 3, 1 for AND. Then you got 4, 1 for AND. No, 4, 1 is your exclusive OR, your EOR in 6502. So you can see here where you can have multiple values for one opcode, which I never knew. I always thought an opcode got translated into the same value, but based on the addressing mode, which I'm not familiar with, I just know it's basically how things get loaded in from memory and operated on. So somebody out there could probably has a better talk on addressing modes than me. In the upper right-hand corner, there's the opcodes for the Game Boy CPU, the LR35902. So it's kind of the same thing, but different values. And you can find these nice, pretty tables that has the opcodes grouped together. And then down in the lower right-hand corner, you got your x86 opcodes. So the x86 opcodes are 2 bytes. So 1 byte is 2 hexadecimal characters, 0 through 255. But in x86, you got 2 bytes, so it'll be 4 hexadecimal digits. But you can see the kind of same. They just got them grouped here for adds, ORs, ANDs, XORs. You got one for push and pop. So you can see with x86 you got a lot more opcodes. And yeah, it's kind of surprising. You can look over here on the second byte here. You got your MMX, which I mentioned earlier. I know that came along in the late 90s for doing multimedia stuff. I'm not really familiar with that. Yeah, so that's x86. A lot more. That's where you get into the CISC complex instruction code set. Oh, I did have an example. I'm not going to run it, but so I learned this a long time ago. You can write a program for GCC, the C program. Have one here called demo. It just has one method called main. So I declare an int called I, and then I assigned I42, which I just recently realized that the ASCII value character code for 42 is star. So a star in like is cleany closure, like in regular expression. So a star means everything. So it's like 42 really is the answer for everything. So that might be where they came up with that for Hitchhiker's Guide, because I think ASCII has been around longer than the Hitchhiker's Guide book. But yeah, look up the ASCII character code for 42, and it's star, which means everything. Kind of blew me away there. But you can compile your C program with GCC. I just did this in MSys2. You do a GCC with the -s parameter, and that will compile your program into assembly, the x86 assembly. So you can see all the opcodes in here. You got your main label for your function. You got your pushes and moves and a call to your main right there. And then you can see, let's see here. You can actually see where that 42 gets loaded in to that value. But the point is, you never do see an I. Whatever you call your variables in your high-level programming language, like C, you'll never see that in your assembly code, because it all gets translated down into register values. But you will. Oh, here's the 42, the $42. So we're moving $42 into that value, that memory location right there. So I just think it's kind of cool if you use that -S parameter, you can see the assembly code and the opcodes, which is what this talk is about. You can see the opcodes for that program. I just made a note right there. You never do see the I, your variable name, and 42 is represented as $42. Yeah, so that's it for OpCodes. I just think it's kind of interesting because, like most people, you write a game in your in Game Maker or Unity or even SDL or Allegro, and it compiles directly into an exe or an executable, but you never really do know how that gets interpreted by your processor. So the opcode is kind of what ties, and the assembly language is what ties your high-level programming language into instructions that can be read by a processor. So I just think that's kind of neat. Probably, I'm assuming a lot of people don't know how that gets translated. Maybe people do know about opcodes, I don't know, but I never was really formally introduced. I do have a book. I don't have it with me by my side right now, but I have a couple of books on operating systems. The dinosaur book. Yeah, let me go grab them. Yeah, so when I started second semester in my computer science program at Georgia Tech, we got two humongous books. The dinosaur book. Actually, this is the second edition of the dinosaur book, Operating System Concepts. It's a pretty good book. I think this was I had to buy this because I had to take another course that used the dinosaur book, and it had different questions for the homework problems. So I guess that's how they get you to buy two books. Basically the same thing. They changed the questions for each chapter, but it's Operating System Concepts. This was the 6th edition. So this goes into a little bit of the operation codes and all that, but this is more how that gets compiled into a program, and how that gets loaded into your operating system. Then the other book, I can't remember if this had like a sleeve around it or not, but this book is Computer Organization and Design. So this is a good book for if you want to know more about how the CPU works, the program counter. This is actually a better introduction. Like, yeah, this talks about pointers and your registers and all that good stuff. So yeah, when I got to college, I didn't know anything about processors or data paths or ALUs. So it was a lot to consume at one time when you're also taking like physics and calculus and all the other stuff at the same time. So yeah, I guess that's one thing. It'd be neat if like in high school, and maybe they do it these days. It's been 20 years since I've been out of college. But yeah, get exposed to a little bit more of the lower level stuff, so you're not blown away when you get into a college level computing class. So anyway, that's all I have for this month. We're doing some work behind the scenes, trying to do some migration of the website. The website was temporarily down. I'm going to thank Dylan Wolf for helping get that back up, but we're trying to do a migration, get everything worked out with that. And then planning on next April of 2024 for the next Game Jam get together. So anyway, appreciate everybody out there listening and watching.